Yeah, okay. So, all right, yeah. So this is our electromagnetic wave. They are transverse waves. These are not compression waves like we talked about with sound. And they're traveling at right angles. So we have 90-degree angles in there. Kind of weird looking, kind of strange to get your mind around, but there it is. Now, this is where we talk about frequency and wavelength. Very long wavelengths, radio waves. The waves that actually go to the radio in your car. Television over the air was actually, I know it sounds like it should be TV waves, but it's not, it's radio waves. They're these long wavelength, low frequency waves. And then we have the little tiny, tiny, tiny gammas, I can't even draw them, that are very high energy. Okay, so you've got very, very different wavelengths, very, very different frequencies. Caleb, what are you doing with your phone? Okay, so we've got very different frequencies, very different wavelengths, which means very different energy. High energy waves are what you need to worry about. And if you look on page 521, there's a rough breakdown. I will expect you to have an understanding of, yeah, radio waves are long wavelength. Gamma waves are short wavelength. And if I give you a picture of the electromagnetic spectrum, then I think you can probably figure stuff out. So know some of the basic uses from that chart. Okay, how fast? How fast are you going? Well, there is a speed limit universally. And that speed limit is SOL. Speed of light. Speed of light. We abbreviate that as C if you think back to E equals mc squared. Einstein's famous equation. Yeah. That's a lot of energy. Yeah. So there is an accepted value for C, 2.9979245 times 10 to the 8th meters per second. However, in pretty much all calculations outside very high level physics peoples, we use 3.00 times 10 to the 8th.
99 million miles.
So it's pretty darn fast. So on page 522, we've got sample problem 14A, and what it tells you is that the AM radio band extends from 5.4 times 10 to the 5th hertz to 1.7 times 10 to the 6th hertz. What are the longest and shortest wavelengths in that frequency range? So we are back to our old favorite, C equals lambda V, or lambda F, lambda V. Our V has been replaced by a C because we're now talking about speed of light. So C equals frequency times wavelength, and we want to solve for wavelength. So C divided by F equals lambda. These don't get a whole lot easier than this. Because C is in meters per second, what units will your wavelength be in? Meters, as it should be. So 3.0 times 10 to the 8th meters per second, divided by, we'll do the short end of the range first, 5.4, or I'm sorry, that would be the long end of the range. No, that would be the short end of the range. Whew, times 10 to the 5th hertz. Okay, so we divide our speed of light by 5.4 times 10 to the 5th hertz. We get 0.555 times 10 to the 8 minus 5, or 0.555 times 10 to the 3rd. So 1, 2, 3, so that would be 5.55 times 10 to the 2nd. Meters. That's pretty long. 555 meters long. That's a long, long wavelength. I stand corrected on sig figs. It should be 2 based on the 5.4. So 5.6 times 10 to the 2nd meters. And all they're asking you for here is the range of wavelengths. So then you just take the other number, do the same thing, and you say these waves are between 560 meters and whatever else the other number comes out to, 180 meters. So just looking at the sample problem. So those are pretty easy. I think you can handle those without finishing out that problem. I will assign numbers 1, 3, and 5 on page 523. If you remember when we were talking about sound waves, we talked about wavefronts. So we have some little object here, a little bell or something that's vibrating, and it's sending waves out in a circle. And as they get very far away from the object, we can take a section of those waves and we can say, well, this small section, they almost look like parallel lines. And so we call those wavefronts. We do something very similar with light, and this allows us to do what's called a ray approximation. So here, let's get rid of that now. If we imagine wavefronts with light, and remember, of course, light waves are transverse, not compression like sound waves were. If we imagine that on each of those wavefronts there are lines of little points, and each one of those are sending out their own little circles radiating from each point, we can draw a tangent line, and that's the next wavefront. Because with sound waves it was easy, because we've got, compression, rarefaction, compression, rarefaction. And so we go, oh, yeah, hey, there's a wavefront, there's a wavefront, there's a wavefront, there's a, but it's not that way with the transverse wave. So let's get rid of our...
Oh, goodness.
What?
The amount of times you have to hit undo to get rid of that stuff.
Yeah, I'm just going to erase it. Okay. So here what we do is we look at the front of all those curves, we draw a tangent line to that, that's your new wavefront. Then we imagine placing another set of dots, another set of circles emanating outward, another new wavefront. And this is called Huygens principle. We don't do a whole lot with this other than just know that it's Huygens principle and it's how you imagine wavefronts with light waves. What we do is we use Huygens, and, well, we don't use it. We don't use Huygens. Huygens is used in higher level optics and higher level physics, and you can look at the behavior of light using Huygens. What we typically do is sort of a cheat around to Huygens, and it's called a ray approximation. So you've all seen an image like this somewhere in a textbook. Right? What is that? What is it? It's an eyeball, and it's a light ray hitting an eyeball, which is every time you see something, that's what's happening, is a light ray is hitting your eyeball, and your eyeball is sending signals to your brain to process them. So if we go back to Huygens and we look at that wavefront approximation from Huygens, so we've got a wavefront, we've got dots on the wavefront, we've got each of those dots emitting their own spheres of light, we've got a new wavefront. We draw the ray perpendicular to the wavefront. So the ray originates from one wavefront and goes through that wavefront. Okay? This is called a ray approximation, and you're going to use this when you attempt to figure out graphically where images will form in mirrors. Do you remember graphic vector analysis? Okay. We're going to do graphic ray analysis. It's better than it sounds. Just like with sound, if you recall that intensity varied by the what in terms of distance? The square of the distance from the sound. Light does the same thing. So if we are here and we move to here, the light is not half as dim, it is 4 times as dim. So it diminishes with the square of the light source. And it's really similar to the way sound is treated. Light propagates in all directions also, unless it's shielded or blocked. And because of that, we're looking at surface area that the light hits. There's a good graphic in your book. Just like with sound, where you're looking at the surface area that the light strikes. And apparent brightness is proportional to actual brightness divided by distance squared. This is actually how we work out how far away different suns are from us, different stars, is apparent brightness. We can measure the energy coming from a star, so we can know how bright it actually is, and we can look at the apparent brightness, how bright it appears from our vantage point, and we can work out distance. So it's a useful calculation. So if we have some light source, a bulb or a candle or something else, and we have light traveling out from it, all these light rays, unless that light hits an object, it just keeps going. What is the best evidence for this? Oh, I don't know. It comes up every morning. Sun. Yeah. That light from the sun just keeps traveling until it hits something. So some of that light from the sun hits the earth. It's used to great advantage by green plants and all sorts of other things. A lot of it just keeps traveling. Just keeps traveling forever, as far as we know. When light does hit an object, basically there are two things that can happen. It can be absorbed or it can be reflected. Now what's interesting is that we have partial absorption and partial deflection. Okay, so we will start tomorrow with reflection in flat mirrors, and we will move on to reflection in curved mirrors. That's the real fun. So I anticipate that Thursday will be reflection in curved mirrors, and Friday will be a FIP quiz.